This version allows you to model petroleum fractions. This means we can add new petroleum fraction fluids to the database and model them in our system. Let's take a look at the database. In this case, we'll look at gasoline. As we can see, the fluid type is petroleum fraction, and all we have to do is specify the specific gravity of the liquid and the boiling point curve definition. So in this case, 0.738 for our specific gravity, and the Astom curve has been defined. When we define the Astom curve, as we can see, the software automatically develops the true boiling point curve. If we do not have the Astom curve information, we can also choose to define the fluid using the true boiling point curve, in which case the software automatically generates the Astom curve. Let's pop this away. When we have defined these two parameters, the software then automatically generates all remaining physical property data. This allows us to quickly add new fluids to the database and model them in our system. We've taken this simple model and we have assigned the fluid as gasoline. The inlet pressure is 2 atmospheres, and at the outlet we have a design flow rate of 2 kilograms per second. If we look at the heat exchanger, we are removing 790 kilowatts of heat from this shell and tube heat exchanger. Let's take a look at the results. As we can see, the fluid at the inlet of the heat exchanger is in 2-phase, and we have removed a sufficient amount of heat to fully condense the fluid, and as a result is leaving in liquid phase. If we look at the inlet pipe, it's in 2-phase. It's applied the Friedel correlation automatically, and you can choose from 8 2-phase correlations. Let's look at the outlet pipe. We can see the software has automatically detected that it's in liquid phase and it's applied the appropriate correlation, in this case the Darcy loss correlation. If we look at the chart tab, we can see the line resistance curve and the duty point. One of the other new features in the software is the ability to view the performance curve for control valves. Let's take a quick look at an example. So here in this case we have water with an inlet pressure of 3 bar gauge. It's at 15 degrees C, and the outlet pressure is 0 bar gauge or 1 atmosphere. If we look at the control valve, it's a pressure controller controlling the pressure to 2.2 bar gauge. It's the static pressure we're controlling, and it's upstream of the valve. The valve in this case is a 3-inch butterfly valve, which has been assigned in the database. Let's take a look at the performance chart. Here we can see the curve relationship for the valve and our duty point on the curve. If we look at the results, we can also see the calculated CV and the percentage opening of the valve. We have also improved the layout of our models in that any input or results information we display in the flowsheet is now displayed in table form. We have also added a new deposition velocity correlation. Let's take a look at a settling slurry system. In this system, we have an inlet pressure of 1.2 atmospheres, the carrier fluid is water, and the solid is sand. The sand concentration has been defined as CV volume percent, and we can also choose weight percent if we wish. And the solids concentration is 10%. Let's take a look at the results. So the software has automatically calculated the deposition velocity and the CVD deposition velocity. If we look at the chart, we can see our duty point on the settling slurry pipeline resistance curve. If we wish to change the deposition velocity correlation, we can do so by selecting Options, Calculation, Settling Slurries, and you can see our Oscar and Turian, our new method. This just represents some of the new features in Fluid Flow version 3.32. For further information or to avail of a free trial, please contact us using the following information.